In this lecture, we're going to explore how the different pharmacokinetic parameters of a one-compartment model following intravenous administration are related to each other. The one-compartment model has two primary parameters, volume of distribution and clearance, and a derived parameter, the elimination rate constant, which is inversely proportional to the half-life. The primary pharmacokinetic parameters are related to how the drug interacts with the animal and are independent of each other, which means that one parameter can increase or decrease without affecting the other. On the other hand, the value of K elimination and half-life are directly related to the values of the two primary parameters. A change in either the volume of distribution or clearance will change the value of K elimination and therefore the half-life of the drug. The volume of distribution is a measure of the extent of a drug's distribution through the body. Mathematically, it can be considered the constant that relates dose to the initial plasma concentration resulting from intravenous drug administration. Conceptually, the volume of distribution is a hypothetical volume of fluid through which a drug distributes. If a drug is administered at a particular dose, the concentration will be lower the larger the volume of distribution is. Clearance is the parameter that reflects the body's capacity to remove a drug and is related to the pharmacokinetic processes of metabolism and excretion. Conceptually, clearance can be considered the volume of blood that is totally cleared of drug per unit time. Here we have drug, actually red food coloring for the purposes of this demonstration, that has distributed throughout a volume of fluid that represents the volume of distribution. The empty beaker on the left represents the clearance, so the volume that will be scooped from the solution and replaced with clean fluid. In this way, the concentration of the drug decreases over time. Now let's see what happens if the volume of distribution changes. If a concentration has a small volume of distribution, its initial concentration is relatively high, and so is the amount of drug eliminated for a given clearance value. On the other hand, if a drug has a large volume of distribution, the initial concentration will be relatively low, and less drug will be eliminated for that same clearance value. Now, what if the clearance changes and the volume of distribution stays the same? The value of clearance determines how much drug is eliminated from the body for a given drug concentration. The smaller the clearance, the less drug is eliminated. So the rate at which a drug is eliminated from the body is dependent on both the volume of distribution and the clearance. Clearance is the constant that relates the rate of elimination to the drug concentration in the plasma, whereas the volume of distribution determines what that concentration will be for a given amount of drug in the body, which is the dose immediately after administration. Rearranging the terms slightly, we can bring together the two parameters which are constants. And we see that it is the ratio of clearance to volume of distribution that determines the value of the elimination rate constant. And it's the elimination rate constant that relates the rate of elimination to the amount of drug in the body at a particular point in time. And remember that that amount is constantly changing as more and more drug is excreted from the body.